Hi everyone, so for this video I will be talking about continuity and the intermediate value theorem. In order for a function to be continuous at point C, the following must be true. First, f of c must be defined, meaning the function must exist when the x value is c. Looking at this graph, there is a hole at f of c, therefore this function is not continuous. Secondly, the limit as x approaches c on the function f of x must exist, which excludes the endpoints because endpoints have one-sided limits. This graph has a function where the limits of x approaching c from both the left and right exist but are not equal, so c is not continuous here. Lastly, the limit as x approaches c on the function f of x must equal f of c. This function is continuous except that f of c exists someplace other than on the function, making it not continuous. Basically, a function is continuous if you can draw its graph without picking up your pen. There are many easy mistakes that are made, so here are a few things to double check. First, make sure all three requirements are met when determining the continuity of a point on a function. It is easy to see that two of the requirements are met and to want to move on, but all three must be true. Second, ensure that you find the correct left and right-sided limits so you can get the correct answer. If you are given a function that is usually continuous, but you accidentally calculate the left and right-sided limits to not be equal to each other, then you will be thinking that the function isn't continuous, even though it is. Lastly, in order for the intermediate value theorem to be applicable, the function must be continuous, and this must be proven before continuing, which is a step that many people, including myself, tend to forget to do. We can determine whether a function is continuous by looking at its equation. We'll start off with y equals 2x squared plus 6. First, we want to look for a denominator. If the function does not have a denominator and is linear or a parabolic function, then the function is continuous. And in this case, we have a parabolic function without a denominator, so this example is continuous. Now the function may have a denominator, like in this example of y equals 2 over x minus 3. So first what we need to do is set the denominator equal to 0, so here we have x minus 3 equals 0. And when you solve for x, you get x equals 3, and this is a possible point of discontinuity. Now we need to look at the interval that's given, so specifically for this problem we are given -2 to 2. Now our possible point of discontinuity of x equals 3 is not in this interval, so we can deem it irrelevant and the function is continuous on this particular interval. Now, what if we were given a different interval, like -4 to 4? So now that x equals 3 value, that possible point of discontinuity is in the interval. Then determine if that point fulfills all three requirements stated earlier that makes a point continuous on a function. If so, the function is continuous, but in this example, the function does not fulfill the requirements because the limit does not exist. I figured this out by looking at the graph and saw that the limit as x approached 3 from the left was -infinity, and the limit as x approached 3 from the right was +infinity. And therefore the function is not continuous. So you may be given an absolute value or a piecewise function. For absolute value functions, you have to figure out the x value where the functions are split, and for piecewise functions, those values are usually given to you. So for this example, that value that splits the functions or splits the two equations is 0. So now we want to plug that x value into each equation. So for this specific example, we get 0 plus 2 equals 2 and 0 squared plus 2 equals 2. Now let's say we had a different first equation, let's say x plus 3. Then that would generate two different y values, 2 and 3, which signify a point of discontinuity. However, for this example, the same y value is generated, so the function is continuous. The intermediate value theorem, or the IVT, states that if a function is continuous on the closed interval f of a to f of b, where k is a number in that interval, and c is in the closed interval of a to b, there will be at least one point where f of c equals k. The IVT also says that when 2 points on a continuous function are above and below the x-axis, then there will be at least one x-intercept. This means that in order to connect the points a f of a and b f of b, the function must cross the x-axis at least one time. However, this basic analysis of the function does not reveal how many x-intercepts there are, just that at least one exists. This same idea or strategy can be used for any horizontal line as well. Let's say we look at the horizontal line x equals 3 in place of the x-axis. What you would look for is on the function you want at least one point where the y value is greater than 3 and one point where the y value is less than 3. This then means that there is at least one point where the y value equals 3. Once you know the IVT is true for a function and a horizontal line, you can then find the x value where the function crosses that horizontal line by setting the function's equation equal to whatever y value is desired. So if we're looking at this graph here on the screen with the x-axis, you would set whatever the function's equation was equal to 0, and that would tell you how many and where the x-intercepts are. Now if we use the example where we have the horizontal line for x as x equals 3, then you would set whatever that function's equation was equal to 3, and that also will tell you how many and where, like the x values of the intercepts for that line of x equals 3. Thank you so much for listening. For more information on continuity or the intermediate value theorem, see the pages listed here in your Calculus 1 with Pre-Calculus 2nd edition book.